Why CRNs? And why are CRNs a Canadian thing? Just Canada. Nowhere else in the world requires a CRN. It's strange. But it's a good question whose answer can best be gleaned by contrasting how Americans build a piping system versus how Canadians build a piping system. So what is pressure piping? Well, a pressure piping system means a system of pipes that is used to contain a gas, vapor, or liquid under pressure and includes any boiler, pressure vessel, or fitting connected to such system. So let's begin the contrast between USA and Canada by contrasting how Americans build a piping system versus how Canadians build a piping system. There are standards for construction of pressure-related equipment, and particularly piping systems. The American Society of Mechanical Engineers, also known as ASME, has developed many standards through its innovative committee process, and the one we will focus on for the purpose of explaining why CRN is ASME B31.3 process piping. An American, before building a process piping system, has to design it, and they have to reference the safety standards. And the requirements of B31.3 require a certain level of experience with the standard, because these standards are complex and do take quite a lot of time, even years, to understand. The qualifications of the designer are found here in paragraph 301.1. Now, before we go on to the component part, a P&ID diagram, also known as a process and instrumentation diagram, is created by the PE for the piping system, showing the interconnectivity of controls of a piping system. After the owner and the designer are satisfied with the P&ID, other drawings are, this drawing and others are stamped by the PE, and components are chosen. When choosing valves, instrumentation, fittings, and vessels for a B31.3 piping system, careful attention is paid to whether the design is listed or unlisted. For example, a listed flange will be found in Table 326.1 of ASME B31.3. This flange standard is called ASME B16.5. An unlisted component would be an eccentric reducer, for example. I'm just going to go back here and we'll just take a quick look. You can see B16.5 here. Now, B16.5 standard has pressure temperature ratings, it has materials of construction, and even dimensional diagrams. So it's a complete standard. Compliance with that standard means automatic compliance with B31.3. And there's no need to really do anything except make sure that they're designing the flanges to that standard. Now, an unlisted component, such as an eccentric reducer, where an unlisted component is clearly defined, you can find in paragraph 304.6.2, where it says eccentric reducer is not in accordance with paragraph 303 shall be qualified as required by paragraph 304.7.2. Oh, what a mouthful. Well, what that means, 304.7.2, essentially means that there is another option for you to qualify your parts to that standard, and that involves some degree of testing, destructive testing, or finite element analysis. That's what FEA means. Now, after the components are found, whether listed or unlisted, and they're determined to be compliant with B31.3, the PE approves the drawings for construction, because in the United States, a professional engineer, a licensed professional engineer with a valid engineering license and insurance, can approve drawings for construction. These are the approved drawings. Now, then the piping system is built. Now, if the piping system, the process piping, B31.3, is law in a certain state, and there are only a few states, a handful of states in which process piping is law. If it is law, then sometimes a government inspector has to come by for the final commissioning and go through a checklist with the owner's inspector and make sure that everything is good. Canadian system. Now let's take a look at the Canadian system and contrast it to the American. Now we start out pretty much the same. The design is made by a professional engineer with experience and knowledge in the code. It's a B31.3 system. Components are chosen. Components are chosen for their ability to do the fit for purpose, fit form function for the design, and valves, instrumentation, fittings, and vessels are all chosen. And the same sort of care is taken regarding listed and unlisted components, and these components are determined to be compliant with B31.3 by the experienced piping system designer. Now, this is where everything differs. But now comes the first extra step that differs from the USA, and frankly, from most of the world. The PE needs to check that the components for the piping system have CRN. The PE, the professional engineer, or PEng we call them in Canada, also has to determine the proper administrative path to obtaining a CRN for the piping system, P&ID, by navigating each provincial and territorial regulation. For example, a piping system is defined in Ontario as having an internal volume, not counting vessels and heat exchangers and valves, of 1.5 cubic feet or greater, while Alberta, Saskatchewan, and a number of other areas define a piping system as being greater than 17 cubic feet volume, internal volume. This is excluding the vessels and the heat exchangers and valves. These safety authorities indirectly currently regulate and control all industrial expansion across the country of Canada by being the exclusive approver of piping systems and piping system components under the CRN regime. And we all know that most factories have piping systems in them. They also have the rights that Canadian licensed PEs don't have, given to them by the regulations. So regulators have special rights to approve drawings for construction, engineering drawings for construction, while the private sector engineers with the similar or even better qualifications do not have this right. This can happen in part because Canada's engineering organizations do not coordinate or lobby. For each province and territory, it's important to also determine exemptions from acts, regulations, ministers' orders, directors' orders, guidelines, and newsletters. These are all relevant and must be understood. But why CRN? We haven't really answered this. Canadian engineers lack rights. This is essentially why we have CRN. It comes down to rights. Canadian engineers don't have the right to approve non-exempt B31.3 piping system designs for construction unless approved by an authorized safety authority. Now, thinking about pressure vessels in the United States, companies that have the right to build a pressure vessel are companies that have, for example, a U-stamp shop. So they have a quality system that was audited by the ASME National Board, and they are now permitted to build vessels. However, an ASME authorized inspector from outside a third party, someone who doesn't necessarily work for the company but could work for the company but is separated and objective, has to inspect the vessel. This is law in most states of the United States. In Canada, this is law for piping systems, not only power but process piping systems, and it's law for fittings as well. Now, in Canada, like I said, B31.3 is law everywhere, and in the States it's not law in too many places. So the OEMs in Canada, people who provide components that are used on inspected piping systems, whether they're instrumentation, vessels, fittings, valves, or anything else, filters, steam traps, etc., they all need CRN if they're not exempt, and there are exemptions, and the exemptions are checked through these documents here, or by checking the websites here and looking at the regulations. Once these guys all send their designs to the regulator, they get approvals, and then the system designer can use those parts in the PNID and can submit the PNID to the government, and the government then approves the PNID. So there's 2 levels of approval here. The system is then built, but because piping code is law in every province of the country, every piping system has to be inspected. Now, what is the effect of CRN on industry? Why improve the CRN system? Well, first of all, CRN introduces a certain risk to a project. Projects in Canada have a big downstream risk, as CRNs are required not only for piping system design, but for all of the non-exempt pressure equipment and components. Delays, missed items before inspection, etc. are all part of the risk. Bottlenecks is another concern. There are about 100 to 120 engineers in total and Certificate of Engineering Technology holders who are employed by the safety authorities across Canada, holding up construction, rejecting innovation, and acting in a way that slows down innovation and construction and essentially puts Canadian jobs at risk. Disunity is another thing. Across the country, the safety authorities do not necessarily communicate with one another to share their technological insights, their code suggestions, and safety findings. And I have found that the safety authorities don't typically attend process piping or power piping code meetings, but tend to focus on the pressure vessel code meetings. And only in that case, we are seeing directors going and not the staff that are actually using the code every day to issue CRNs. Some government officials are prescriptive when it comes to interpreting the code, and they're not obligated to listen to or bring into law the code interpretations that are found by the committees in the in-between publication phases. So they occasionally give hassles. Our firm knows all the bad actors. We hardly ever hear about the engineers at the safety authority that are good and tend to approve things without so much hassle, and they're more helpful maybe to the manufacturer. Competitiveness. We've noticed that the safety authorities tend to compete with one another. The whole reason why we have so many safety authorities is competition. At the very beginning, it was meant to be a unified, centralized process, but that never happened. Finally, accidents do happen, sadly. This is a picture of an accident. I think it is the Sunrise propane facility exploding, but I'm probably wrong, so I'm not going to commit to that. I made this slide a while ago and I neglected to note what it was about. But anyway, it's an accident that happened, and lawsuits are rare. The safety authorities are under administrative law, and it's very difficult to prosecute under administrative law. And admission of error by the safety authorities doesn't seem to be something that's ever forthcoming. So essentially, when something goes wrong, there's a response by the safety authority, but it's very slow in the coming. And if the safety authority gets sued, then they settle, and part of the settlement is that they don't have any blame. And of course, then that isn't a disincentive to provide clear guidance as to the nature of the hazard and how to prevent having this accident in the future.